In this video, I want to graph these systems of inequalities. And the idea here is that to satisfy this system, I have to be a point that makes this statement true and this statement true. So what we're going to do is we're going to follow our procedure for graphing each individual inequality, and then we're going to see where they overlap. In our last video, we saw some inequalities using graphs that were lines and other things, and we're just going to follow that process again. So I'm going to rewrite this one on the next board so I have a little more room. So in that first problem, we were asked to solve x minus y is greater than or equal to 4, and x plus y is less than or equal to 6. So what we're going to do is let's graph this inequality by itself, just pretending it's a problem from the previous lesson. And I'm going to get y by itself, and so I'm going to take x away from both sides, so minus y is greater than or equal to minus x plus 4. And now I need to multiply both sides by a minus 1, so y is less than or equal to x minus 4, remembering that our inequality symbol changes if we multiply both sides by a negative value. All right, so now I can graph this inequality. So my y-intercept is minus 4. My x-intercept is pretty easy to tell at 4. I could also just use the fact the slope is 1 and go up 1 and over 1. I use a solid line because that's a greater than or equal to. And I'm supposed to shade the part that is where the y values are less than that. So this part. And again, we could pick a sample point. And so that would just be the graph of that first inequality. So now let's graph the second one. Taking x away from both sides, I just get y is less than or equal to minus x plus 6. Another line here with a slope of 1. Y-intercept is 6. And again, I could go down 1 and over 1. Excuse me, a line with a slope of minus 1 this time. But I'm going to use the other y-intercept. Excuse me, the x-intercept, the other intercept. This is where I should edit something like that out, but we're just going to let it ride. All right, and again, I'm shading the part that's under the line, and we could test. I think the origin would make a great test point here. 0 is, in fact, less than or equal to 6. All right, so that's what the solution to this one would be. And so now the idea I have is, what happens if I try to solve them both at the same time? Well, that would involve graphing them on the same set of axes. And so I have my blue line. And I have my red line. And this point here where the lines intersect, that definitely solves both because both have an equals to. That point would actually be the solution to the system of linear equations that I get if I just replace these with equals to. So now I see 1, 2, 3, 4 places I could possibly shade, and I need to shade the place that solves both of these at the same time. So I like to imagine I set this one right on top of this one. And if I thought about it, well, this side of the blue line is shaded blue, and this side of the red line is shaded red. And so if I lay them on top, this is the region that would turn purple, right? Because this part's shaded red, this part's shaded blue, but this is the region that's shaded both red and blue. And again, we could pick a sample point, and something like 5 comma minus 1 would work. You plug that into both equations, and it has to work in both at the same time. So that is 5 comma minus 1. All right, so I plug that in. I get 5 plus 1 is 6, which is greater than or equal to 4. I plug it into the second one, and I get 5 plus a minus 1. Well, that's 4, which is less than or equal to 6. So now I definitely know I've shaded the correct region. If I pick a point in one of the other regions, I won't get a true statement in both places. So let's look at the origin. That's going to solve the red equation, red inequality, but not the blue one. So I plug it in, and I get 0 plus 0 is 0, which is less than or equal to 6. But when I plug it into the top inequality, I get 0 minus 0 is greater than or equal to 4, which is a false statement, so that region's out. What I like to tell students is if I can give myself some kind of reason to shade an area just based on where things overlap, I'm going to shade that, and then I'm going to pick one sample point just to make sure. So we've solved number 1. Let's see if we can figure out number 2. That top inequality would be a circle if I looked at an equation, x squared plus y squared equals 4. So I'm going to draw a circle of radius 2 centered at the origin with a dotted line because there's no equal to here. And when I draw this circle, I see a region that is inside the circle and a region outside the circle. So if I wanted to pick a sample point, I could pick one inside or one outside and see what happens. If I pick the origin, I get 0 plus 0, which is less than 4, so I'd shade inside the circle. If I was just graphing that top inequality, I would shade inside the circle. And if I think about that, that makes sense. When x squared plus y squared equals 4, I get the circle. If x squared plus y squared is less than 4, I'm on the inside of the circle. If I make this a greater than, I'd be shading the outside of the circle. All right, so if I just graph that by itself, I'd be shading the inside of the circle. That's not my solution for the whole system, but I'm just going to make kind of a note saying, hey, x squared plus y squared less than 4, that's shading the inside of the circle. And now I have a line. And I'm going to get y by itself. Y is larger than minus x plus 1. So it's a line with a y-intercept at 1 and a slope of minus 1. I need to draw it with a dotted line. And if I was to graph just this inequality, I'd be shading the things above the line. And now I definitely see the parts where they overlap. Above the line and inside the circle is where I need to shade. Now, the line itself is dotted and the circle itself is dotted. But I get that kind of like, I don't know, less than quarter moon kind of wedge there as the solution to that system of inequalities. And I really do like thinking about it as being inside the circle, but above the line. All right, 2 more systems of inequalities to go. Let's do this one together, and then I'm gonna let you try this one. So here, I have a circle of radius 3, and I'm shading the inside again. So a dotted circle. And anything inside the circle will definitely be a solution. And then this is the inequality y is greater than or equal to x squared. So I have my parabola. And I'm not even going to graph it outside of the circle because I'm only interested in things that are inside the circle. And in fact, this is a solid line because that's an equal to, and it's on the inside of the circle. The points where my parabola would hit my circle, those aren't solutions because they're on the circle and that doesn't contain equality. Y is greater than or equal to x squared. I need to be inside the circle but above this parabola. So that's this little shape. It's curved and doesn't include that arc there. All right, pause the video here and give this one a try. Okay, so there's another circle. This time the radius is the square root of 2. X squared plus y squared equals r squared. It's a little more difficult. The square root of 2 is about 1.414. So I'm just going to do my best to draw a circle with a radius that's about the square root of 2. And I have a line. X plus y is less than 2, which is also the line y is less than minus x plus 2, taking x away from both sides. That line has a y-intercept at 2 and a slope of minus 1. And so this is a challenging problem in a certain way. I need to shade points that are outside of the circle, right? Not on the inside, and points that are below the line. Y is less than minus x plus 2. And so that's this region, where I'm under the line and outside of the circle. So it's like someone shaded below the line and then just punched a circle out of it. And so there we have 4 systems of inequalities. And one thing we could do, if we weren't sure, I could pick a point in every region and try them in both inequalities. And only the points in purple would work in both.